Hey, John here. Let's work out let's finish up our warm boot routine today in our BIOS, okay? Now, the extensive documentation that we have to work with here, one sentence right here. It's a testament to how awesome and how simple and how clean all this really is to do. Right? One sentence is really the only doc we have to go on. CPM system must be reloaded or must be loaded from the first two tracks of drive A up to, but not including the BIOS or CBIOS if we hacked it up, which we're doing. All right. So what does that really mean? Well, it means we have to reread the CCP and the BDOS right here. And we have to put them wherever it is they go, which right now we're starting our operating system. The CPM base is D400. Okay. Now, if we go into our memory.asm file, this is the CPM base variable that we define in there. We can move it up and down and stuff like that. But given our current firmware setup and everything else, as long as it's greater than C000, we're okay. And we have plenty of memory up here right now, so this is fine. Let's not move it. Let's not create any complexity. Bottom line is, what do we know? The CCP and BDOS are a non-zero size. This green region right here is a total of 16K that is read by the firmware bootloader off the SD card. And it comes off the SD card out of partition 1. The first 8 meg of partition 1 is the image of our entire file system that we're using for our CPM disk, which is our drive A, okay? And this green region down here matches the green region we saw in the memory map above. So what we really need to do is read whatever portion of this first 16K out of the 8 megabyte image here from the SD card and put it into the memory starting at D400 through E9FF. Okay, so that's the BDOS and the CCP. So we just got to, that's all we got to do, all right? How hard can it be? We'll see in a minute. Actually, it's not that bad, okay? So there's your documentation for warm boot. We've seen the rest of this before, because when we're done rereading in the operating system proper, I guess you could say, the other things we need to do is make sure that our 0 page is in order, okay? Now, before we dive into this, let's take a look and see what they did in their MDS BIOS, the sample source code they give us in the distribution, right? So if you scroll down to where the warm boot routine starts, you get a little bit of an insight here, all right? So there's their boot. Basically, it matches ours. Then here's the warm boot. Notice the very first thing they do. They're going to use... They have to establish a stack somewhere. Now, they're going to use the DMA buffer that starts at address 80. I've been using the directory buffer that's up in the BIOS, but maybe it would be better for us to go down here and do what they did as well. And why not? Well, it'll be consistent. So I'll make that tweak as we go. Point is, when you enter into the warm boot routine, you have absolutely no idea how you got here, other than you're assured that the BIOS memory, the memory, you know, everything above the BDOS, no one has touched that. Allegedly, right? Unless the thing is crashed and somehow wandered off into here, right? But the bottom line is, this is what we can assume. Therefore, we have no idea where the stack pointer currently is aimed. We don't know if it's safe to use it. We have to reestablish a stack, okay? Now, I'm not going to use the stack that we reserve for the read routine, because as we're going to see, the warm boot routine has to call the read routine. In fact, if you scroll through here, what does it do? They're going to set up a loop, and they're actually going to deal with recovering from read errors from the floppy disk in their logic here. I'm not going to mess with that. I'm going to just put the loop together and assume everything's going to be fine. For now, right? So what do we do here? They're going to set the DMA address. This is an equate that points the BC register pair in, this is 8080 assembler here. LXI is extended immediate to load the register pair BC with this label here, which is going to be the beginning address of where the CCP belongs in RAM after the, it gets reread by the warm boot routine, okay? So you're going to see it's going to use its own BIOS subroutines. This is why we had to write the read routine before we use their code as an example on how to write our warm boot, okay? So we're going to call the set DMA, we're going to make sure we're using the right drive, we're going to set the right track and sector, and then we're going to enter into a loop like they do here, and we're going to read one sector at a time. Every time we've read a sector, if there's an error, we're going to stop and print a message and just halt. If there's not an error, what we're going to do is we're going to do the same thing they're going to do here. We're going to move the DMA address forward by one sector size, change the DMA address, and then go back in and around our loop and keep going one sector at a time. Once you've advanced your sectors beyond the end of a track, for us, that is 4 sectors per track / SD card block, you have to not only advance the sector, you have to advance the track number as well. Okay, and then you got to reset the sector back to 0, but I think that should be straightforward, right? And that's all there is to it. And then RD sec goes back to the top of their loop. So this is going to read in one sector at a time for as many as is necessary to copy the CCP and the BDOS back into RAM. Okay, when it's done, it's going to go to do the usual go CPM routine. And what do they do down here? I don't know how closely we looked at this before. They reset the DMA. Yeah, we looked at this because I remember saying, well, they did it, so we should do it, even though it seems superfluous. They reset the the 0-page vectors and jump back to the beginning of the CCP, okay? Now let's see at what I've done to the file that's sitting here before I commit it. So we can look at this sum total of all the changes before we wander through the source code and see how it fits into the bigger picture. This one's pretty straightforward because literally what I'm doing here is I'm simply rewriting and replacing this one function in the BIOS. Now I have some equates to help me out along the way here, which have to do with how many sectors do I need to read off the SD card, what track number, the SD block number, track number, do they start on, and at what sector does it start on. Okay, that's what these things do here. Then I use them in my routine. It's going to look a whole lot like theirs. I start off by reestablishing our stack pointer, and I've changed my mind 2 or 3 times, and I'll probably change it again now, and we'll set it to 80. Okay, no big deal. You just have to make sure that your stack is somewhere legal and reasonable and not going to interfere with your ability to, come back to life after this warm boot is done. You just need to make sure it's okay because we're going to use the stack down here. We're going to call subroutines and stuff, okay? The bright stuff is no change at all, so that's the debug that's been there all along. And then down here, you can see I removed the comments that remind me I need to reload it and replace it with the code to load it. And you'll see this is the Z80 version of basically their same code down here. What do I do here? First thing I do is I mark the SD buffer track as invalid. Okay, and when we talked about the read routine, this is probably not necessary for me to invalidate it here, but I wanted to, hit it with a big sledgehammer and make real sure that there's nothing hokey and weird going on. So by doing this, it guarantees that when I call down here the BIOS read routine, it won't try to recycle or reread, reuse some old data that might still be around in the SD card buffer, okay? So that's why I've done this up here. And I do the same thing they did. My initial logic to make sure that I'm using read from drive A, start at the first track where I know the CCP must be, and the first sector, and put it where I need to load it into, which is at the CPM base. And we've seen that before. That is where the CCP starts. And it's the same address that we go to in our go CPM routine, okay? And once that's done, I use the BC register as a counter, and I count up to the number, or I count it down to 0, actually. from the total number of sectors I want to read in off the SD card down to 0, and I call BIOS read. If there's a 0 is in the accumulator, and it's also in the flags at the time that BIOS read exits, right? If that's okay, we go down here and keep going. If it's not okay, I replace the it's dead now message with a different one that simply says that the warm boot read operation has failed and reminds you that you need to press reset to reboot. And I go back into our endless loop here. And when we successfully read a sector, what I'm going to do is, because I didn't really save the DMA address, the track number, the sector number, and any of the registers per se, I'm going to use the values where I know the BIOS saves them. And this is only okay, in my opinion, because this code is officially part of the BIOS and can directly access those things, right? If I change the meaning of these variables, and I'm going to change them in this same exact file, in the read routine or in the set DMA, set track, and stuff like that. So I can actually reach in there and grab them because I know that's where they are. I know exactly how they're used. And if I change them, like I said, I'll have to remember to come up here and change this code as well. And that'll be easy to do because my technique is to just search for the labels of things that I'm messing around with if I'm going to change their meaning, and I'll look through the entire file. Usually I'll grep my entire source tree to make sure that no one touches these areas and labels. But because there's a dot in front of them, these are local labels. And somebody asked me about the dots, I guess the other day on one of the comments on a YouTube channel. The dots, due to the assembler that I'm using, okay? Some assemblers do this, some don't. I'm using Z80 ASM, and in that assembler, if you start a label with a dot, it becomes a local label to the file. So it won't expand out, it can't be touched by other files that I might include within this file, or even if this whole file is included by some different file, no one can see these labels that start with a dot, unless it's code that's actually in this physical file, which is the retro.asm file. Okay. So what's my point here? I'm going to go grab the DMA address that the last read used, and I'm going to put 128 in the DE register, and then I'm going to add that to the HL register, and then I'm going to put it back into the BC register, because that's where it has to be in order for me to call set DMA. I mean, yeah, I suppose I could cheat, not call set DMA here, and just poke it back into the disk DMA variable. But if I do that, then I got to concern myself with whether or not set DMA might be doing something else in addition to simply saving it in that location. And by now, I hope we all know that it does do something else, and that is it prints out a debug message. Okay, so I'm going to go ahead and do this, because if I have debugging on, I want to see that somebody called that, and we'll turn it on and watch it go in a minute. Okay, so what do I do then? When I'm done with that, I've advanced the memory pointer to where the sectors go one at a time. I need to advance to the next sector. Okay, so I'm going to load the sector number. Now, I don't need to load all, 16 bits, because in this BIOS and on this drive A from the SD card, I'm guaranteed it'll only be a value from 0 to 3. So even if I stored 16 bits, if I load it like this into a single register, the accumulator like that, I'm going to get the least significant byte because we're little endian, all right? So that gives me the low end, even if it's 16 bits has been stored in there. I'm going to add 1 to it because I want to go to the next sector. I'm going to AND it with a hex 3, which means if it has become 4, then wrap it back around to 0. Okay, when that happens, I got to go to the next track, right? So after all this has been done, if I have a non-zero value, then I know that the current sector that would be read in will be 1, 2, or 3. It won't be sector 0 because that's handled down here, right? So I'm going to go down here and I'm going to read it in. If it turns out that I just finished reading in sector number 3 and I added 1 and it went to 4 and came back to 0, it would fall down here, and that's the point I need to advance our track number. Okay, so if that's the case, what I do is I say grab the current track number, add 1 to it, and store it back into the location. Okay. And then I call BIOS set track to reset it. Okay. Now, I don't check to see if I've gone too far here because, I mean, logically I can't, because I know I'm starting near 0 and I'm only going to go up a couple of tracks, like 32 at most, right? Because that would be the whole 16K, and it's not going to read all that. It can't, in other words, wrap around off the end of the whole disk. It just can't, okay? So I didn't even bother to check for that situation. If it did wrap all the way off to the end of the disk, what that would suggest is that I've made a mistake up here when I loaded the sector count into the BC register up here, okay? That would simply mean I put too big of a number in there. So that's a bug up here, right? So I'm not going to bother with that. We're going to assume everything's perfect. Always a safe gamble, right? So after I've set the track, I need to make sure that the accumulator has a 0 in it, because I'm going to fall down here into the same logic that I go to up here, where the accumulator has to have the proper sector number in it so that I can put it in the BC register pair and call set sector routine, just like the other ones, right? So I've advanced the DMA, I have adjusted the sector, and optionally I have moved the track number forward as well. And at that point, I'm going to pop BC, which is, remember, has the count of remaining sectors that need to be read in. I'm going to subtract 1 from it. And then I'm going to ask, is it 0? If there's nothing else left, I'm going to fall through to the Go CPM down here. Okay. And if it's non-zero, I'm going to go back to this warm boot loop code up here. Repush the counter and read in the sector, and advance, read, set, count, advance, read, count. Okay. So that basically is the entire warm boot routine. Okay. Let's look down here at what happened to our Go CPM routine. Another comment from somebody on the YouTube channel told me something that I never knew. I then went and poked around a little bit and found that there are things that are really never mentioned in the alteration guide, that it is mentioned in the Andy Johnson Laird book, right? And by that, the issue is this. It turns out that there's a couple of problems when it comes to reloading the current disk number from page 0 during the warm boot process. I mean, I remember I copied this right out of the alteration guide. The original version, I just simply put 0 into the C register and said, have a nice day, and we're going to go. Putting 0 in the C register means that the CCP should start up and drive A should be the currently selected drive, period. If you have multiple drives in your system, the alteration guide suggests that what you do is you go grab the value out of the 0 page that has the current disk number that's being managed by the CCP and the BDOS down there, okay? And you try and reselect that drive, right? Now, we'll play around with this in a minute, and I'll show you what's wrong with this and why I just simply say, I'm going to blow this away, forget it. I mean, the bottom line is we only have one drive anyway, so no matter what, we have to reselect drive A. But let's look and see what's wrong with this code, because if you play around with this BIOS and you start adding other drives, we start getting to the point where we're going to use the other virtual drives on our SD card, because I'm going to have 16 of them all out of that one partition if I want. I can build another board and I can plug in more SD cards. I can do all kinds of stuff, right? So ultimately, we do need to make sure that we understand what's going on here, right? So we'll take a minute and look at that because it's really germane here when we look at the code in a minute. Now, the diff proceeds down to the bottom of the file, and this is where I put my label. This is the stack that I'm using right now. I put this label at the end of my scratch directory buffer that's in the BIOS. All right? Now, as you saw in the alteration guide, they use the DMA buffer in address 80. for their stack. And I mean, I honestly, I get torn by these things. What is the right decision? What's the best possible thing we could do? I go back and forth even while I'm talking the last 5 minutes. I think I'm going to leave it here. Okay? And the reason I'm going to leave it here, I'll explain this when we look at the code directly in a second here. Okay? Let's open up the file and go back and look and see what's going on here. All right, so didn't touch anything up here at all. First thing you saw on the diff was this, okay? And let's make sure we understand what these things are. Because there is this big assumption right here, which turns out it's always going to be true. What this logic here assumes is that the CPM, the CCP, the data that we're going to load from our disk and put it back into the memory to reload the CCP and the BIOS, will always start at the beginning of a sector. The very first byte of a sector on our disk must be located in an address in the RAM that is a multiple of 128. Okay? Because we're going to read an integral number of sectors, and we're going to put that data into the memory of our system. Okay? And this is all using integer division, and will fail if this assumption is not true. Now, it turns out that if you use the move CPM and the sysgen process and all that, what you do is you specify where the memory is that the that CPM is supposed to use. Now, we have the source code, so I'm actually, as you know, we're going to just assemble the entire source code right into this one file, all in one big image. So in theory, we can make this thing start at any address we want, and it would assemble. However, if this does not start at an address that's a multiple of 128, the stuff we were just looking at down here will fail. Okay? Now, it's not normal where that is ever going to happen. Here's the listing file from the last time I ran the assembler on this. So when we do an include on memory.asm, it's been a while, so let's review this. I mean, I haven't even updated the file. Oh my God, it's from last year. Yeah, 4 months ago. Since I last touched this thing. See where I say mem equate to 60 here? This is very similar to how you deal with CPM when you're doing a sysgen or a move CPM and stuff like that. What you do is you normally express it in round kilos. And you give it a number. I want a 48K CPM. I want a 60K. I want a 63K or whatever. Usually it's in round kilos. And in the logic in here, this equate is expressed in kilos. And this is the value that represents the address where CPM will start relative to this number here. This is a weird, in my opinion, notion that they use to specify the size of, your memory where the operating system's supposed to go. This minus 7K thing, but I kept it. It's just part of the charm of CPM, right? My point is the value here matches what you do when you're going to do a move CPM. I'll leave that as a manual read to the viewer if you want to know more about it. The bottom line is, the way this system is built, oops, I went too far, guarantees that this assumption is true because my mem setting, which is what you just saw, the math that is used to generate where CPM base goes, is always a multiple of 1K, which is a far greater alignment than a mere 128. Okay? So what's the point here? Well, the point is, if I know where BIOS boot is, and I know where the CCP starts, which is this, remember BIOS boot is the very first byte. Oh, that's not true. Oh, that's bad. I just found a bug in my program. Where this is supposed to be the first byte of our BIOS, not BIOS boot. So I don't know. I played the Jedi mind trick on myself. Why did I do this? That's totally wrong. And I'm editing a readme. I must have did view instead of vi. Okay, this makes more sense. it turns out it'll still work anyway. If I read too many, what would happen is that it was using the BIOS boot label, which is up here, right here, which means it would have read too many sectors. Now, when I tested this, it all works fine, but even if with this mistake, it would continue to work fine, provided that I never try to modify any of the memory up in here up to this point, okay? Because it would be clobbered, right? And I don't, because there's no variable stored up here, but it's still wrong. So let's go with that fix, right? So the point is the number of sectors equals the number of 128-byte units of data that are fully consumed by the entire CCP and the BDOS, and that would be the differences in these two addresses here. Honestly, that boot thingy is so small that this would have rounded down to the right number anyway, because I actually did check the resulting values and I counted these sectors out and it came out right. So I accidentally succeeded, but wow, are those things difficult to debug when stuff moves around in memory later on. So I'm glad I found that. So moving on, what is the first track number off of the SD card that we need to read from? All right. Well, we know that when the flash boot ROM runs, our first stage bootloader, it reads the whole 16K at the beginning of the SD card into memory, starting at load base. So if we take that, if we know that CPM base is where the CP starts, and that has to be at an address greater than load base. Okay. Therefore, this minus load base divided by 512 and rounding down will be the very first track number, because each track has 512 bytes on it, that has the sector on it that we need to use to start loading our the operating system back in. And a similar logic for the sector. We use the same subtraction, and this time we divide it by 128, and we're looking at a modulo 4 type of thing here. By handing it with 3, we throw away all the other bits, and this is the same thing as saying modulo 4, and that'll give us the first sector. Because we know it's aligned to a 1K boundary, because of what I explained earlier about the way we configure the memory, it really better be that the first sector that we read is sector number 0. And it turns out that the track number, following that logic, a little back of the envelope check here, better be an even number. Okay? Because if it's odd, then that means it's on a 512 byte boundary that's not a multiple of a K. So we can sanity check these values. The greatest sanity check, by the way, is if it boots and it actually runs, you probably did it right. Because if you did it too much or too little, the whole thing will get all messed up. Simply because the OS source code will not, or the source code, the binary load image will not have been reloaded correctly. All right, so these are the symbols that I'm going to use in our. We've actually already seen the loop that says starting at this first track number and this first sector number for this many sectors. We go in our loop, and that's the logic you saw down here. Okay. Now here's where they loaded their stack pointer with address hex 100 to use the DMA area that's down here in the 0 page as their stack during the warm boot process. Yeah, we could do that if we really wanted to. I'm going to go ahead and leave it up here in the directory buffer that we allocated up here in the BIOS, okay? Now, the reason I don't want to mess around with anything south of CPM base here is because there are commands like DDT and load and the save and the move CPM and the sysgen process and stuff like that, where what you do is you run a program that puts stuff into the TPA. And when you're done with it, and you can move it around, you use these offsets, it's a bit of a rigmarole. If you read up on how to use the assembler that comes with CPM, it'll explain how you basically do the linking process or the loading process by hand. And you take Intel hex files and you load them into the TPA and you say, move this up here, move that one down there, and you put all the pieces together. And then you go back into the operating system, and that's the key part. You go into, you're back at the command line, on drive A or whatever, and you use a save command that says save this many sectors in the TPA into a disk file called, whatever you want to say. Okay? Now, it's not normal to do a warm boot of your system between the point in time when you load all this stuff into the memory and the time that you save it into a file. But it would be nice if I could warm boot and not touch anything in the TPA, and after the warm boot is done, be able to save memory out of the TPA onto the disk and know that the process of warm boot didn't wreck anything in there. Okay, for debugging reasons and anything down the road, so we don't get disoriented, because we're going to forget that we made a bad choice if we make a bad choice here. Okay. Now, by using the what I call my warm boot stack, which is the directory buffer that we allocate solely for the use of the BIOS, I know for an absolute fact that it's garbage and whatever is in there is utterly worthless during the warm boot process, because by definition, I'm reloading the BIOS, therefore it cannot possibly be in use, nor can its contents be even remotely relevant. Therefore, I can clobber it and do anything I want with it. Now, earlier on, my first draft, what I did is I used the CPM base as the address of where to put my stack. And the idea was, if you don't mind ruining the TPA, you can put your stack here and work your way down. It's not going to hurt the BIOS, it's not going to hurt the CCP, not going to hurt the BIOS, not going to hurt the warm boot process. However, it will clobber some data up here. And if your goal after a warm boot is to be able to look at the TPA all the way up to the CCP line here, it'd be nice if we leave that in a clean state. All right, so that's all there is to that. All right, I want to leave that in there as a note to myself to mention it here, but I'm going to delete that now, and we're going to go ahead and leave this in the BIOS directory buffer thing. Okay, and I got a little note up here to remind you and me next time we want to clown around with this, not to mess with this thing. Now, I know what you're thinking. We have a stack. Why don't we use this stack? Well, we don't use this stack because warm boot, remember, comes along down here and it's going to call. Oops, I went too far again. What's it going to do? It's going to call the BIOS read routine right here. What does a BIOS read routine do? First thing it does is it saves the current stack pointer, and it reloads the stack pointer to use that BIOS stack area. That's why we can't use it here, because we're going to call BIOS read, and it's going to use that for its stack, okay? So remember whose stack belongs to who and what your subroutines are going to do, so you don't end up clobbering all your value variables and stuff like that, all right? So that's what we're going to use this during the warm boot process, okay? Debugging, if debugging's on, we're going to print a little message. We're going to set all these things. I just went over all that. It'll read in and go fine and hunky-dory. If it fails, we're going to go back and we'll seize it up right here with a message. You can just press the reset button to try again. Someday maybe we'll make it auto retry, but we can deal with that later. There's the advancing of the sector and the track and the wrapping up when it's done. And when it is done, we fall down to the go CPM. Okay, now, bird's eye view here. We can see the whole routine and not just some diffs down here. So there were no differences here. This resets the 0 page, okay? Resets our DMA address to 80. Because it said to do so on page 52 of the alteration guide, even though it does appear to be superfluous. We dump out our, level 3 debug if we want to. And, okay, so before what I did, as I did this, followed by that, and then I said, go back to CPM. And then I got to talking to somebody online, and I said, the byte in address 4, they pointed out to me that the most significant 4 bits, I should shout out your name, I really should. In fact, it's this one right here, develop IT, develop it, I'm not sure. as they point out, something in the that the documentation doesn't tell you. As the current disk drive in that byted address 4, okay, includes the currently selected user number. So if I put that in register C, like I have been doing in its entirety, then, as I say, whoa, I never knew that, but oopsie, let's take care of that, all right? What happens is I would have, if I don't do this, in other words, and I just blindly put the value that's in memory address 4 into the C register and go back to start up CCP, I am not only selecting drive A, I'm specifying that user number whatever is supposed to be set as well. Now, that could be a little disorienting, so the recommendation was to do this and set the user number to 0 and retain whatever the currently selected drive is. Now, if we do this, we see a certain problem occurs. Let's go ahead and put this code in here, just for fun, and run it all, verify this whole thing works. We'll see what's wrong with it, and then we'll go back to what I was doing on day 1. Now, look, no matter what we put in here, and whatever we try to do for portability purposes and things like that, right now, today, we only have one drive anyway. So no matter what we put in here, we have to end up with C equals 0, followed by go restart CCP. Thank you very much. Okay? Now, the reason we want to get to the bottom of this ultimately is because if we want to support more than one drive, and we want to do a warm boot, and if I do a warm boot while I'm on drive B or drive C, it'd be nice to wake back up and be on drive C or D or whatever, okay? So ultimately, we'd like to fix this code up here. But even as it is right now, if we zero out the user number so that it wakes up somewhat more sane, and we retain this disk number, we're going to see a problem that I'm going to show you in a minute here. It made me laugh the first time that I saw this happen. I was like, this is crazy. So, oopsie, what did I do wrong here? Junk at the end of line. Oh no, I broke something. 292. Oh, I turned this back on. And oops. That's not how you write that instruction, is it? You say and you give it the number because you can't and anything but the A register. Therefore, that is the way you're supposed to write that instruction. My bad. Ugh, too used to running modern CPUs these days, you know. All right, so as I showed last time, we create our whole file system from scratch each time if we really want to. I guess I don't have a world rule in here. Let's go ahead and rebuild the whole thing so we know we're clean and reinstall into our retro image file here a perfectly clean copy of the file system with our newly compiled BIOS and everything else, okay? So you can go ahead and copy this thing back over to the one or something like that. And what did I do? I said the block size equals 512 bytes. But you know what? It really doesn't matter. I don't believe, because it's going to do 512 byte blocks anyhow. So this is a little bit overkill. Is it capital or lowercase? I can never remember. I think that's what it is. Actually, you know what? We don't have to care what it is, because I just remembered I actually have a rule in here for this. I just type make burn, and there's the line of what I'm supposed to do right there. Okay, we saw this last time. It's been a few days. I can't remember everything. And let's go ahead and get our terminal back on here. Put the SD card back in the retro and hit the button. So it looks like the debugging is currently off. So far, so good. Because we didn't run any of the warm boot code yet. So all we did is we added code to the system and didn't touch it yet, okay? If I hit Control-C right now, this is warm booting, okay? So I just ran the warm boot routine. It silently succeeded. You know, I don't know if it really did or not, but I do know for a fact that if we run DDT, where is our CCP starts? Oh, I think it's at like D400 or something like that. It's at D400. So if I dump out D400 and I do this to E000 or something like that. We can watch what comes up in here. I guess I can't really tell what this is. I don't know if this is the CCP or the next. This is DDT. That's a message from DDT right there. My point is, I know that DDT moves itself way up into the high memory because it's designed to debug programs that run starting at address 100. Therefore, it would not be very useful if DDT itself stayed down there. So this thing is definitely clobbering the CCP, which is why you have to warm boot to get out of it. There's actually me typing in the command. That must be where its keyboard buffer is or something like that. And that's at DB60. And eventually we'll run into the BDOS up here. Where is my memory map? BDOS starts at DC00. And the DDT moves itself up to this line right here, up to F base. Okay, it can't overwrite the BDOS because it needs the BDOS to access the keyboard and the disk and stuff like that to load and save files. So, what was that? D6. Yeah. So basically, DDT can't touch anything over. I guess something around here. Oh, there's next PC. Boy, is it? This is an interesting question. I never really analyzed this that much. So that goes up to DC00. I misread it. It is DC. So this is DDT up here, potentially. And it's not until you get all the way up here to DC00 right there where we know you can't touch this if you want a warm boot when we're done. Okay? You can clobber the BDOS if you want. But you can only do that if you don't need to use it after you've clobbered it. Okay? So if I hit Control-C while I'm in DDT, it definitely rebooted. And we just saw that, to the trained eye anyway, that we know that it clobbered the CCP in order to make that happen. If we run it again, we can say go to address 0, which is the entry point for the warm boot. Okay, this is another way to terminate DDT, just like G0, and just start running. Well, what does it do? Well, there's a jump to there, from there, into the warm boot code in our BIOS. So warm boot finally works, right? So if we're going to run Adventure, this was another program that clobbered the CCP, as you recall from last time we were playing around. Blah, 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 yada, yada, yada. Sure, show me the directions. Blah, 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 blah. We know now that we go to building and we can look around. And oh, I don't want to play anymore, so I want to quit. Do I want to quit now? Yes. So I hit this. And remember before, this thing seized up in our warm boot routine, and now it comes back to life. So we now have warm boot, which means we have a fully functioning CPM system with a read-only disk. As it is right now, it will act as if this disk has the right protect notch set, or covered or exposed, depending on the kind of disk that you're using, right? So this is actually pretty cool. You can certainly play almost any game. You can't save your settings, and we can't edit files yet on CPM until we create a write routine. But with a warm boot running, we finally have enough of the system working that when your programs are done, it will terminate correctly, okay? Now, I know it's working because I already tested it. Let's go back and take a look at something here. Let's really make sure everything's okay in our various routines here. Okay, let's look at our Go CPM. What did I do? I commented this routine back in. Okay, so what does that mean? Because I'm going to reload the current disk that is set by the CCP or the BDOS or whatever part of CPM manages that down here after a warm boot, I'm going to tell the CCP to reselect that disk when the warm boot's done. So let's see what happens if I select drive F. All right, makes perfect sense that there is no drive F. So I got an error on drive F. Oh, I can't select drive F. How smart is the CCP? I submit it's not very smart, because it went and stored that into the 0 page. If I go ahead and warm boot now, I'm stuck. Every time it warm boots, I am permanently screwed. Okay? This is worthless. So their example code in their BIOS is not optimal. Okay? The only way out of this is Hotel California here. We got to front button this thing now. I mean, it'll come back. I mean, you hard boot the thing. But no, this is just bad. Okay? So that's why I'm going to go ahead and leave this with an F0 right here. The only other thing you could do in here, I suppose, if you wanted to retain the disk, if the disk is valid, what you would do is after you throw away the user number here, you would check to see if A is greater than the maximum disk number. And if it is, then you know it's invalid, in which case you could basically set it to anything you want that is ultimately valid, because a user did something dumb anyway and they can't proceed anyhow. So what you could do is simply set A to 0 up here if A is greater than 0, which is why I just did this. And for now, that's what I'm going to leave in the BIOS. This is what I'm going to commit for this video here. And then we'll come back and revisit this when we add more drives or something like that. All right? So that's the problem with the way that is set up and the way it's given in the sample BIOS code. Let's go back up here and turn on the debug routine here. Because, until you actually know and you see this thing go and you know what all the sectors are and what's going on, you don't really know that it's working. Okay? I mean, there could be all kinds of false positives coming into play here. Definitely could be, all right? And what do I mean by that? Like we just saw, and I'll leave it to you to verify it. Let me know in the comments below if I'm wrong, that, DDT overwrote CCP, but it did not overwrite the BDOS. If my warm boot routine is wrong and it comes up short a sector, you saw the code at the beginning of this video. It used to be long by a sector, although I think it rounded it down and it was okay. Anyhow, if that's wrong, and it comes out that it doesn't properly reload all of the BDOS, then sometimes it might work, like when DDT ends. But another app that might overwrite the BDOS, it won't be able to reboot. It won't be able to warm boot, I should say, afterwards. So you could have all these weird problems, And that's why I want to reboot this thing. We've seen this before. It boots up. It reads the entire disk while coming online after a cold boot. And you see the cache working. So 1 out of every 4 times we have a cache miss in the usual way. All right? Now, let's just hit Control-C and watch the warm boot process take place. Let's skip a few lines so I can scroll back and easily figure out what's going on here. First time I did this, I was like, what the heck is it doing? I was confused. Oops, scrolled too far. So let's make sure that everybody understands what's going on here. Okay, so when I hit Control-C, it said that the BIOS read routine was entered in here. Okay? I set the debug level to 1. I did not set it to 2. And because I did not set it to 2, it doesn't print the little message out about how BIOS warm boot had been entered, right? I set it only to 1 because I only want to see what's going on with the reading of the disk right now. I didn't want to print all the extra stuff out, okay? Just so you realize why you don't see that extra message right now. Okay, so I hit Control-C, therefore it's going to warm boot. The read routine is entered. And it's going to read a sector on disk 0, track A, sector 0, and it wants to put it in D400. That makes sense, all right? That we are starting on a sector number 0 because we know it's a round kilo address, okay? This is an even number, like I said before. And D400 is where the first bytes go of the CCP, if you remember from our memory map over here. That's this D400 right there. That's where the CCP starts. So far, so good. And remember, I invalidated the SD buffer cache. So even if it had a sector from this track, which it does not, because nothing will ever read from tracks down there other than our own code custom that we do in the BIOS. okay? The BDOS will never look south of the directory on the disk. So it's going to miss the cache, it's going to read it in, and then it's going to say there's sector 0123, and then it goes to the next track, 0123. So you can see it reading in one sector at a time in order, which makes sense because that's what it's supposed to do. You see the track numbers going up, A, B, C, D, E, F, 10, 11, 12, yada, 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 and it'll eventually finish up. And what happened here? So this is what threw me before. What I was doing is I was watching the DMA addresses, okay? And we see it go all the way up here, and it reads in at E900, and it reads in at E980. This is why I know that my math, even though my code was off a little bit, I knew it rounded it down because I was checking to make sure that it read in all the sectors it needed to refill this area all the way up to E9FF, which is the last byte of the BDOS region. Because EA00 is the beginning of the BIOS, right? I wanted to make sure it read it all and wasn't short, it wasn't long. So what I was doing is I was watching these lines here. Well, E980 plus 128 bytes in hex is 80. So E980 plus 80 is EA00. So this is the very last sector that should have been read in, and that is the correct address where it should have gone. So who the heck is poking around up here all of a sudden for no reason whatsoever? Remember what happens when we're done with a warm boot? We start up the CCP. What does the CCP do when it starts running? It reads the entire directory in, starting on track 20. This is it going from 20 to 3F. That's what it's doing, all this extra reading in there. Totally, I was like, oh, I wasn't even thinking. So, I always make sure that everything makes sense, because I actually thought there was a problem in my loop, and that I was just like haphazardly reading stuff and throwing it all over. Look where all the DMA addresses are here. When it gets done with everything up to EA00 or E980 or whatever it is right here, okay, all of a sudden, every time it reads, goes into F2BD, right? We saw this a couple of recordings ago. If you look at the listing file, remember that, what was that, F2BD? We look in here, and we look for what F2BD is, A, B, C, right here. This is the directory buffer. Of course, it's going to be putting all the directory sectors in there. When it's rebuilding, it's the ALV. That's what it's doing, right? It's going to scan through the ALV. So luckily, we're not using the stack anymore. By the time we go from the warm boot into the CCP, because as soon as we do that, obviously it will have overridden that block there. All right. So I think that pretty much covers all the issues and getting the warm boot routine worked. And yeah, I found a bug even while I'm talking about it here, even after I tested it. So there might be another bug hiding out there. So you might want to look it over and let me know. I eagerly await comments on YouTube below the video here. All right. So what am I going to do? I'm going to leave the weird go to CPM turned off. I'm going to go ahead and leave the stack set there. There's the warm boot routine, and I'm going to put the debug back off again because I don't want to see it. At least right now. I'll commit it with this turned off. That way we can boot it up and play some games and stuff and have some fun without too much debugging noise. Keep doing that. What a habit. So thanks for watching. I'll see you next time.